Hello, everybody. The topic for today is how do you connect the processing, structure, property, relationships in engineering thermoplastics via engineering tools, specifically rheological tools. So, I want to introduce to my parent company, Sabic. Sabic was established in 1976 with about 31,000 employees, 50 countries of operations, and the revenue is about 46.6 billion according to 2022 brand finance, and it has about world class plants worldwide, 66 plants, and is one of the top two chemical brand will today. So to dive in further, there are different businesses, and we are one of the world's most diversified chemical business. And we have a petrochemical business. The business where I belong is specialty business, is agri nutrient business and metals. Uh, to focus specifically on the specialties business, um, we have unique polycarbonate lexan copolymers, we call it LNP, and polyethylamides materials and copolymers for niche specific applications, and is a very good special materials. Today I have a great opportunity to showcase uh, specifically some of the unique materials and how do you do connect the structure, processing, property to your product performance. In a nutshell, if you want to look at the specifically on the LNP PC copolymer specializations, if you look at it, we have methods starting from weatherability, structural materials. If you need a metal with a good friction, wear resistance, if you need a sustainability concepts, in terms of the impact flow, and the fire safety, flame toxicity. Today, we have most resins for different applications. Today, I would like to focus on this particular section: flame, smoke, and toxicity. And specifically, I will talk more about a specific polymer called CFR. It's a unique PC copolymer resin with a unique N group, and it's a branch system, and we call CFR. The full form is clear flame retardant materials, means that it maintains transparency like polycarbonate, yet it flows very well, and also it has a unique anti-drip properties for flame for electrification market. So how do you characterize those kind of interactions through a simple rheological technique? So I just want to give you a flavor of rheology, dynamic testing. So if you look at it, this is a unique rheometer. Let's say a stress control rheometer in a parallel plate. You put in the samples between the two plates, a gap of let's say 1 millimeters, and the bottom fixture can oscillate with a velocity, and also impose a deformation to a sample. The deformation imposed, the torque imposed is measured by this force transducer, and you can calculate the for example, if you put a strain to the material, it can calculate the stress given by the sample, and then you can calculate strain rate, and basically we input the deformation strain to the material, and then it calculates the stress given by the sample for a given temperature. So you can back calculate a material response in terms of how viscous it is and how elastic it is for a given temperature. This is a very powerful tool. To elaborate further, uh, I put in a sample. Let's say I'm going to put in a sample well beyond a glass transition temperature. For example, you want at a processing temperature of a thermoplastic, like a polycarbonate, let's say 3 degrees centigrade. So I imposed a deformation via strain, and the sample tested temperatures give me a stress, and it can give you viscosity but you can deconvolute the viscosity into two components, say loss modulus and storage modulus. So these two important parameters here. So think about, you have a sponge soaked in water, correct? So if the end of the day you squeeze the sponge, and the sponge wants to recoil back, come back to the equilibrium to original shape, and also water is spilling out, even the resistance given by the water is called viscous component. The resistance given by the sponge to deform back, whatever deformed come back to original shape, is called elastic component. So those two components can be calculated through this measurement. And then what is the difference between these two components via phase is called phase angle. The phase angle is an important parameter as well to determine how elastic, how viscous the component is. And by knowing these parameters is very important, because if you test any complex material like a polymeric material, you need to understand the elastic component, viscous component, to connect back to the processability and structure, and also thereby at the end of the day the final product state. Right. So these are important concept. So what we care about is usually the OEMs, the customer care about what is the process time involved in that, what is the cycle time, what kind of process. For example, you take it here, you have a process material time scale. Every polymeric material will have a characteristic material time depending on the temperature you process that, and also your process time. And it has to, all depending on how fast I process and what is the material time of that material, what is processing. For example, here you can look at the center here. So I have a parameter here called with the shear rate or angular frequency and time scale. You can see the shear rates relevant to the injection molding process. If you look at the shear rates relevant to the injection molding process, uh, it also spans from 8,000 to 10,000 shear rates. So you have to see the process time scale and the material characteristic time scale. So to understand the whole time spectra, how the metal behaves in the solid state, for example, how long-term behavior, long-term creep, physical aging, molecular architecture, you have to test the materials at that particular time scales or relevant shear rates. And more importantly, this entanglement concept I'm talking about process is very important for all the processes, the properties which we're going to attain. For example, you have a bloom molding process. For example, for bloom molding, you need a better melt strength. So it might have a certain characteristic time scale and the process time scale. So you have to balance it out in a way it works in the process. And also when you go to the high shear rate, very small time scale, you can also talk about very local molecular motion, and it's more viscous dominant state. So for example, you can span whole decade of time, the whole time scale via different methods. You can have the concept of time, temperature, superposition to rheological methods. We can test different temperatures and frequency and try to superimpose, get a master curve. And also you can use kind of a creep relaxation methods to figure out, relaxation methods to figure out what kind of architecture is there and how this is different from a linear material. For example, you have a branch system or any other topology. So you can also do steady shear to figure out the viscosity function of shear rate, how shear thinning the material is, what the viscosity drops at what shear rate. A dynamic mode give you a lot of rich details on the molecular nature. And of course, high shear rheology, we call calorimeters, will give you the viscosity ballpark for the process. So at the end of the day, you are able to make a process with a certain property with the innate chemistry what you haven't had. So if you take any textbook, you say that the entanglements and long-chain branching, for example, so say entanglements in polymers. See, you have a zero shear viscosity as a function of molecular weight. So you say that the molecular scale to the slope of 1. Beyond certain molecular weight, it scales to 3.4. It agrees with most polymers, thermoplastics out there. But when you have a branched polymer, the scaling tend to differ in a different way, and that's why this differs, because the entanglement density and the way that relaxes is different from the linear material, so the scaling is differing. And the more importantly, you take a solid state, you have a mechanical strength as a function of molecular weight. So you can say at the very low molecular weight region, there is no entanglements, almost zero. Then beyond certain molecular weight, you have some entanglement, viscosity goes up, and you have a polymer property. A property means that you have a certain strength and ductility, particle ductility, and you have some kind of enough entanglements to have a specific property of strength. But by keeping increasing viscosity, entanglements, you can't able to process. At the same time, you need to process too. So you need to have enough entanglements, and same time you need to process. So there is always a balance to understand. So the reason I'm bringing up long chain branching, I'll show you next slide. So first of all, I like to explain what do you mean by long chain branching is. So when you have a molecular weight, when you have a chain, the arm is longer than the critical molecular weight. For example, for polycarbonate, the critical molecular weight is approximately around 5,000 gram per mole. So if the branch are longer than 5,000 gram per mole, that means I call this long chain branching. So if anything less than 5,000 gram per mole, I would like to call it a short chain branching. So the long chain branch is very unique in terms of the rheological properties. Same time, short chain branch will also have unique properties. Everything has pros and cons. We need to understand it, right? So when you take this melt flow index, which is long chain branching. So melt flow index is something in data sheet people always like to show. When you have a low melt flow value, that means the molecular weight is higher. When you have a high melt flow value, the molecular weight is lower and it flows very well. Correct. So, for example, you have a piston which is certain weight, you have a material to put through a die. When the material flows out in 10 minutes, for example, it flows out a lot, you weigh material, it says material flows very well. That means you should have a low molecular weight. And at the same time, the material flows very low, it has high molecular weight. That is general concept. But the problem here is when you branch materials, the rheological properties are different. The melt flow index is only one data point, right? So right here, for example, you have a complex viscosity as a function of frequency. You can see the branch material, the polycarbonate, for example, here, the viscosity is very high, out of very close to 1 atom higher, correct? And then the melt flow index is correspond to the frequency of 10 shear rate. You can see that it's only one data point. It shows that my branch material has a very low melt flow. But when you take it to the higher shear rate and extrusion condition or initial molding condition, you can show it actually, you see the viscosity catches up with high shear rate, correct? So the way rheologically it is made is like you like to unravel in entanglements at the particular shear rate and try to catch the viscosity at high shear rate, but same time it have a low viscosity. It helps in some process as well. So this is pretty unique, and a long chain branching can be very uh, tricky sometimes. It's pretty difficult to say, even though the melt flow is low, it may or may not process, but actually it flows very well in the high shear process. So that is something which I want to point out in the terms of long chain branching. So just to connect the concept here, so we have a set of unique copolymers, special copolymers starting from EXL. We call that based with some siloxane comonomers, and we have HFD materials, all copolymers. I want to focus on the CFR, as I told you earlier. It's a clear flame retardant materials. So it goes through a lot of applications, as you can see here. It starts from the computer housings, and it can talk from television bezels within wall materials, and also the more importantly, I would like to focus on the electrification market here, which is basically you need to have a certain property like a flame to pass a standard regulation test. to have the good rating so that it can serve electric. For example, EV charger. These needs of all safety. So nowadays, all electric chargers, electric cars, EV charger is very critical, and the materials you supply should be have a good frame properties. Same time, it has to have a certain features which could be on par with polycarbonates, correct? So for CFR, the clear frame retardant material, you can see this is the regulation test for electrification market. It's very strict regulation test. You have a motor flame bar and have a Bunsen burner at the bottom. You burn it for 10 seconds and so and have another exposure. The thing is, if the if you have a very good rating, it should not drip and has to self extinguish on its own. So but sometimes it can have a rating that it drips, it could burn the cotton at the bottom, the rating could be different. So the best way for this kind of application is to have a rating very good, so the chemistry should help, so it should not drip. And sometimes the rheological tools are very important to understand the chemistry, just what kind of structure you have, what kind of process you get. And also the similar thing is a horizontal testing. It's a plaque of 150 millimeters. Here you can see when you put a flame, very strong flame at the bottom, so the hole created should not be greater than 3 millimeter here. And it should have a very stringent behavior. The material should able to pass the test and should not form a hole. And just an example here, if you have a standard polycarbonate, when you put a flame, it starts burning at around 320 degrees, not 320, 420 degrees centigrade. This is your picture we took it. When you have a certain additives or certain materials with FR grades, that could able to self-extinguish and also act as an anti-dripping agent. So to connect with that, with the concept here, so I want to focus on two unique polycarbonate copolymers where you like to connect the effect of N group on the anti-dripping properties of polycarbonates. For example, you have a UV active N group. So I have a polycarbonate backbone. You could have a UV active moieties in the backbone or in the end capper, where you can shine the UV light certain time and it form a cross-linked material on the surface so that it could help the flame ratings. Or I could also have a material, the backbone, maybe it's branch you can say, and this blue dot here is end cappers, unique end cappers, where it likes when you begin to burn, it likes to knock off this and try to form a crossing so that it helps in anti-dripping properties. So I would like to explain these two polymers. First, let's focus on the uh, thermally cross-linkable polycarbonate copolymers. Then we can talk about the UV cross-linkable copolymers. So the first topic I said earlier is the branched polycarbonate with reactive N group, where it helps to the N group helps to anti-drip properties. N group will help in terms of chemistry, where the N group would like to cross-link and builds a viscosity, molecular weight, so that it stops the drip under flame. So my job here to tell you how to characterize that material to understand what kind of crossing is going on, how you characterize how it flows. For example, here, just to compare, you have a linear material and you can branch it lightly or you can branch it heavily. You can add more end cappers and you can also have a different architecture. So for example, as I told you here, you have the red dots at the backbone, the triangle could be the branching agent, and then there's an end capper. When you go beyond processing, it begins to form a crosslink. So how do you characterize this crosslink is that if you take a rheological method, image state, put a sample between these two plates and try to do a temperature ramp going from 280 to all the way up to 420, you can see these particular special PC copolymer like to build viscosity or modulus so that it can stop the flame propagating act as an anti-dipping agent, whereas a standard polycarbonate would like to decrease its viscosity and modulus as a function of temperature. Only at a certain temperature it like to begin to decompose. And this is the melt state. So now I make a part. I like to compare the impact strength of the material with the branching agents, the branch involved. So you say the linear branch is almost a similar ductile properties, but if I like to branch it more, you might end up in losing some ductile properties as well. So it's very important to connect the how much of branching is needed, how much of end capper is needed to serve a particular application like electrification. So the part of the bottom is also derived from this dynamic rheology, where I plot the phase angle as a function of a complex modulus. You can see the inflection point here. You can see the linear to branch to blend. The inflection point, it's almost similar. But if you branch it heavily, I call hyper branch, it shifts to the left. So when I back calculated this, we call this inflection the plateau modulus. When I back calculate the entanglement density of it, I can clearly show this hyper branch material is affected. So in affected means the entanglements per chain, or not per chain, entanglements for a network will be lower. When I say entanglement density will be lower, thereby it could affect the bulk property like impact. Now, so the same concept here. Now I talked about branching, hyperbranching. Now I talk about branch PC also to see how it behaves in terms of the rheology. G prime is the elastic component. G prime is a loss component. You can see with the angular frequency. You can see in a classic test literature, it goes to the slope of 2. It's the elastic component. But the point I'm trying to make here is that the linear material behaves like this. The branch material does not want to behave like linear material. So because you see the crossover point is uniquely different for a given frequency. That means, and the slope also varies. That means, what are the architectures when you go beyond linear, start polymer, HO, it does affect your so-called material relaxation in time. Thereby, we have to see how we can exploit those kind of behavior for application. So different architectures can relax hierarchically different from the linear analog. So the idea here is to how to exploit those additional relaxation modes to an application which is viable to commercialize. So for example, here you see that here. You see the hyperbranch material, branch material, the blend of linear branch material and the linear material. So the linear material you can see here, when I normalize the viscosity to show the shear thinning index, how much viscosity drops to shear rate. As a function of shear rate, you can see the viscosity of the branch materials drops much faster, and it drops pretty good compared to linear analog. And you can see the example here. You can say I can make a thin wall part. It's very clean part for a thickness of about 0.8 millimeters. Same time, the end capper, when it's branched, the end capper can serve as a cross-linkable beyond processing temperature, so that it can help the flame properties. So the branching makes polycarbonate flow well while retaining the FR properties. The branch density plays a vital role. I told you earlier that when you branch it, enough is good. When you branch it heavily, it could happen that it could hurt your ductile properties. So so it's very critical to have a balance in this branching in capper and how much you can add, so that you can serve for a purpose of a different application. So that is mostly on the special PC copolymer with a specific end group, which is thermally cross-linkable, to show that it can help in anti properties. Now I slowly move on to another type of polymer where you have a end capper and the backbone moieties, where you have UV active. When I shine a UV light, it likes to form a radical and form a cross-link material. Now, how do you characterize those? And this proved to be a very effective method also to form positive flame properties, and to stop the flame propagation. And my job here to show how do you characterize that UV cross-linkable polycarbonate for to define a formulation. For example, here I say it's a polycarbonate with a UV active moiety. So we have a UV active light. This is a polycarbonate, and then you have a UV light so that it like to form a radical and cross link, and then that cross link we have to figure out how much of crossing we have. Those crossing and potential features can give a good chemical resistance materials. It could impact properties. It don't hurt the impact properties, right way to say it. And also good aesthetics, good flame resistance, good processing, good weathering. So the focus is more on the flame resistance, right? So I talked about cross-linkable material thermally in the previous slides. Now I talk about materials which is cross-linkable in the room temperature itself, because the polymer itself, when you make a part, it has a UV material ready to absorb UV light and form a cross-link. So when we extrude and make a pellets, these UV active molecules are ready to form a cross-link. For example, here the PC is a regular polycarbonate. When you have XPC, which I call cross-linkable polycarbonate, when I have a 2 pass, 5 pass, 10 pass, means it has a 2 rounds of UV exposure, 5 rounds of UV exposure, and 10 rounds of UV exposure. As I keep increasing the exposure of UV light, you can see the buildup in elastic modulus, which tell that there is it's normally at a processing you have a dominant viscous property, but when you cross-link it, materials will tend to become a little bit solid-like. The modulus just keep going up in the rheologically at 3 degrees centigrade. So for example, at 1 radians per second, it can go from 10 to all the up to 100,000. So that means the EV active moieties are easy to absorb the UV light and form a cross-link material. This is evidence to characterize cross-linking. And also, if we compare that with the standard polycarbonate, you have a storage modulus, you have a frequency, right? So even though I expose UV light, but if the same exposure of UV light, you do not see that crossing happening. Only this can happen because it have a UV active moiety. This is in melt state, correct? There is a dramatic increase in storage modulus, indicates the existence of UV active network. So now you take it to the solid state now, right? So you say it now here, I have a material. So I made a part, I expose UV light, then you do this test in a solid state like DMA, where you can see storage modulus as a function of temperature. You can see a linear polycarbonate have for a given molecular weight have a decent TG around 145, 150, and then have a plateau, and then the modulus drops and the structure goes away and it's melt state. And then if you cross-link it, you can see those cross-linkable moieties would like to increase the modulus to some level and try to extend the temperature a little bit more. So for example here, this is the actual flame plaques for the 5B test. You can see that when you have a material with a good cross-linkable moieties and a good cross-link evidence that it does form the flame creating a hole, whereas the polycarbonate does form a big hole. So these crossing networks which is formed would definitely help the flame resistance, and this is a good one to show to see that how effective is crossing density towards a flame. And it's a pattern we filed a couple of years ago, how the particular formulation with a specific N capper the moieties in the backbone and a molecular weight combinations would like to give a crossing and develop a method to understand what kind of the modulus, average modulus will help to form a antidote properties. You can see we figured out that when you take an average of this particular rubbery plateau here, starting from 9 to 10, 12 matters Pascal seem to work very well for a given formulation and how we formulate. For example, I plot this average modulus as function of time to hole. Time to hole is basically when I say pass. So let's say XPC1 formulation, we say 110 is a pass. That means it can withstand up to 110 seconds before forming a hole. and say XPG4, for example, we have a less, probably you can say less amount of UV active moiety. It can only withstand 40 seconds. So I consider this not very good fail. So you need to formulate accordingly what kind of crossing density is needed to pass this kind of product performance. Same time it can process well. So these kind of rheological tools will definitely help to characterize and correlate the product performance. So just to show another evidence here, you can see here, you have a flame resistance, for example. So before UV exposure, you can see the big hole formation. After the UV exposure, you form a cross link. It doesn't want to form a hole. So it's a very interesting material we have. It maintains the ductility flow. The FRPC today can go up to 3 millimeters. It's okay with 5B testing. But if you want to go to a lower thickness, like a electrification market is demanding, these kind of cross-linkable materials can have a big advantage and can help in defining a material for its needs. So I hope I explained the two different concepts here. The same polycarbonate copolymers with thermally cross-linkable N group and a UV cross-linkable N group both can give a good advantage of frame properties while still maintaining the polycarbonate properties. So now you have a now I move to the next topic of I talked about LNP, PC copolymer resins in our portfolio. I also want to talk about our high heat offerings for solving specialties. So we have some unique polyethylamide. The market name is Altum. It's a very high glass transition. For example, if you go to McDonald's or anything, you do see a plastic on it's a very high heat. Most of them could be polyethylamide. So because polyethylamide had a very high heat resistance, and we have a unique materials like we call XTEM, which can go beyond the heat of Altum. We can do chemistry based on what we need. And also we have another material to if customers need an application needs a certain better ductility than the Altum, we can also make chemistry happening with the siloxane type Altum, which could serve as as for different applications like wire and cable, things like that. So the thing is, and also this kind of materials also is a very good flame retardant material by itself. That's a good you call LOI, limiting oxidation index. So this was a very good flame. But nowadays people like to use materials with a PFAS free, and these kind of materials could be very handy to stop the flame propagation, good ratings. And a lot of markets here, starting from automotive, healthcare, aircraft, food contact, what approach is a very niche applications, and these are unique materials for high end of engine thermoplastics. So just to give an example here, so this is a polyethylamide. It can go into applications starting from elasticity, high heat resistance. You can see the food compliance. You can use a lot of aerospace industries because it's a good flame properties. It's very compliant, good stiffness, and it can go to has a lot of fiber optics, a lot of sensor lenses. And we also can make a polyethylamide apart from pellet. We can also make in different forms, like powders, which can disperse better in a UV tapes. Very high definition tapes. You could talk about making a filament in the different formats of nowadays 3D printing and manufacturers very unique applications in different formats, and we can able to make it in different format whatever the way the application needs dimensions are. So at the end of the day, Altum resin, polyethylamide resin is a very good choice as it complies with certain regulation for variety of industries. So this just want to show the high level of polyethylamide, but to taking back to the structure property concepts, I'm connecting back to the viscosity and entanglement again. So you have a polyethylamide. So you can see here the polyethylamide is made of two monomers. One is diamine, one is a dianhydride. So basically meta-diamine and the paradigm. So when you make a polyethylamide with a metadiamine, you have certain properties. When I make it with the paradiamine, you have certain properties. We also see the increase in TG. When I make it with diaminosulfone, different diamine, we do have an increased TG Okay, so you can also talk about TG of 247. If your application demands high TG materials, we can also play the chemistry to make it high materials and much more than that. So end of the day, I'm going back to the fundamental principles here. First principle, you need to have a viscosity as a function of molecular weight. So we have to create a molecular weight beyond certain critical molecular weight, so that you have to have a particle ductility, and same time you can process well and attain certain product features. So when molecular weight exceeds MC, the viscosity also increases significantly. So you need to have a balance. What kind of a molecular weight, what kind of entanglement strength you need to have a property for an application. So again, so same on the entanglement. So as I told you earlier, the molecular weight plays a vital role, and when you make a polyethylamide with a different backbone, like I said, meta to paradiamine, this backbone conformation can have a significant effect on the entanglement density. And then, for example, if I could make it a polyethylamide, like as I mentioned here, with para-based material, because the CRS is for a good chemical resins material compared to the meta-based material. So, but it does affect some kind of properties. So, for application which needs high chemical resins, still maintain close to ultim-like properties, like a para-based metamine, this could be a good choice. So it all depends on how you change the chemistry, how it affects the physics, how it affects the process. We have to understand all these things. So what I'm trying to say, these kind of rheological tools will like to connect the applications for the process structure property to product performance. So I have a couple of other things to show. The thing is, I'm touching back on the rheological tools again. How do you connect the time temperature superposition? For example, here you take a polyethylene resin. I touch with like what 6-7 temperatures. I can create a master curve together like this. So at the processing temperature is more like a thermal regime. So basically G prime J prime means, I told you earlier, it's a storage modulus, loss modulus. I can also say it's a viscosity, it's a decon. So basically I like to say storage loss modulus because it does talk about structure more than the viscosity alone. So if we call thermal regime, that means you're in the processing side of things and you don't get to see a rubbery entanglement effects and more on the segmented effects. But when you check with try to go close to TG is 220 here, close to TG, you can get to see all the regimes and go from the rubbery to the glassy regime. Why this is important? Because I tell you why. So when I take a rheometer, you put the material, you deform the material, certain strain, material response, certain stress, correct? So the reason why it is important, because if you want to understand why there is a change in TG, why there's change in certain product features, you want to know effect of the glassy region. So I will show an example here. So you have a material, storage modulus, loss modulus, right? So in a parallel plate, metal made from the meta-based diamine, and you have metal-based para-based diamine. You see, as a function of the frequency, the thermal regime is kind of very similar. But if you look at the glassy regime, for different frequency, we can go very low up to TG, which is more glassy, and you can see the crossover point of the paradiamine, basically the polyethylamide. Again, I'm going to repack again. Polyethylamide made with the para-based material is different from meta-based material, correct? So if you look at this, the characterization, you can see there is a significant change in the segmental dynamics when you go to the glassy regime. And also, if I back calculate that with the entanglement molecular weight, you can see a significant change in the, so you see the Platter modulus here, right? When you make with the para-based diamine, polyethylamide, meta-based polyethylamide, right? So it does affect the entanglements pretty well. Same time, this kind of materials can have a difference in TG, and the backbone conformations I like to call is at least very important to do these kind of techniques to understand why, so that you can, a smart chemist can do a different chemistry if needed to understand what's going on. So most of the times these tools would help to develop a new chemistry all the time. So So this is my final slide. Just want to show, a polyethylene made with the different formats. For example, you can play with the meta-based meta-based diamine. You can also make a different blends with, for example, here this is the linear material with the branched blend, and try to understand the flow behavior, and also with the 50% of the four based meta and 50% of the para-based meta. You can play with the different material blends it. You can see the melt flows varies from 32 to all the way up to 18. But this melt flow actually doesn't make any sense, because for these kind of materials, what's more important is what's happening at the high shear rate end. What is the processing end? For example, here I have the viscosity ratio from high shear rheology. Let's say I took the ratio from low shear like 100 to high shear to 5000. You can see my ratio is 5.1 for the branch blend. That means 5.1 means it flows very well. Its shear thins pretty good. Whereas if you look at the melt flow values here, it's 12.5. That means it tells me it doesn't flow. But actually, it's not reality. It flows very well. So these kind of architectural effects, structure property effects are very important to understand. For example, a thin wall sensor lenses. If you want to make a fiber optic type material which may have a thin wall parts, so the flow is very important. So we need to understand certain chemistry, structure property correlations through this kind of techniques. So end of the day, the thorough characterization and understanding of these why these things are happening, and going back and forth would help to defend a product for an application. So this is the conclusion I have. So I talked about special polycarbonate copolymers and polyethylamides. So I talked about two different polycarbonates copolymers, which is CFR and is a UV active group and is a thermally crossing group. So both the story here is if you have a cross-linkable moiety in a polycarbonate copolymer, it does help in the flame propagation while still maintaining the inherent polycarbonate properties, which could be a great application for electrification, a platform, you want to call it electrification applications, which we are already providing materials. So the thing here is, the reason I keep saying that it retains the properties of polycarbonate means polycarbonate is very unique by itself, but sometimes polycarbonate has some other issues with frame properties. So these kind of copolymers are very effective. This kind of chemistry is very effective to give extra edge to the polycarbonate. And also we have polyethylamines isomers. I talked about it. The unique viscosity, entanglement, structure property correlations are very important to understand the application needs are. So this is a polyethylamine isomers. You can say backbone stiffness dramatically affects the rheological and mechanical properties. And I also showed that a combination of linear and branch blend flows very well with a reasonable thermal stability when you process. So to conclude, this is our local contact here. Anwad is the business development manager, and if you need any information on the products we sell, because you want to understand more, and he'll be happy to help here. And thank you.